Let's do an example dealing with exponential growth. This is problem number 3 from chapter 1 in the text, and it deals with population growth. And it looks at this example that the book looks at. Suppose that the population of a certain city doubles every 10 years, and that the city starts off with 100 people. In the book, we're told that it takes 260 years for the population of this city, if it continues this way, to reach the population of Earth, which is 7 billion people. And so let's confirm that this is true. And so on the chart here, I just sort of wrote here at the end of the year, so 260 years to reach 7 billion people. And so let's go through and look at this. So first of all, you could do this just by kind of doubling the numbers. But hopefully you can see that that's going to take a long time and be really big pain. And so it's nice to use the math here. And so the first thing I'm going to do is figure out, okay, what multiplicative constant do we need? So 7 billion, if you write that out, it's 7 times 10 to the 9 people. Okay, and what I want to do is, so here's the multiplicative factor. And what do? We start with 100 people. And so I want to know, what m do I need then? So if I take m times 100 to equal 7 times 10 to the 9, my factor of n will be 7 times 10 to the 9 people divided by 100 people. So first of all, the people cancel, and I get 7 times 10 to the 7 for this number here. Okay, and so now let's go and look at one of our formulas. So our formulas, one of them looks like this. So m is equal to 2t divided by t2. And so what do I want? Well, I want to find out what t gives us this multiplicative factor of 7 times 10 to the 7. So I'll take this, and let's go over, slide over. And so again, I'll take this formula here, 2 to the t to the doubling time. So of course, again, our doubling time in this problem is 10 years. And again, I want the m to equal what? So I want the m to equal 10 times 10 to the 7, and I equal that to 2 to t divided by 10 years. And so now what do? Well, what we need to do now is look at this and use kind of our little tricks that we've been using. So right over here, for this 2, right, so there's this trick we have, which is calling this the exponential of the natural log of 2. And so I'll write that exponential to natural log of 2, and then that's again to the t divided by 10 years power, which again, the way we've been sort of writing it is look like this here. So exponential of t, natural log of 2 divided by that doubling time, which we're going to be writing as 10 years. Okay, and so what I want to do now then is take this, so that's 10 years, and so equation is again 7 times 10 to the 7 equals this. So I'm going to take the natural log of both sides, and so I get natural log of 7 times 10 to the 7, and that's over here natural log of this exponential t to the natural log of 2 divided by 10 years. And of course, we know that this natural log of the exponential of something is just this here. And so we sort of wrote it this way because we knew we could do this and sort of get this out into a nice number t. Now this over here, natural log of 7 times 10 to the 7 is just a number. And so I can go through and calculate that. And so we got, again, natural log of 7 times 10 to the 7. And this then equals t, natural log of 2 divided by 10 years. And so what I want to do is I want to isolate the t. So I want to get t, and so that's going to be natural log of 7 times 10 to the 7. And then when I isolate the t, okay, I'm going to be over here, I'm going to be multiplying the top by 10 years and dividing by natural log of 2. And when I plugged into that, I got this number of 260.6 years, which again is what the book was saying. So that worked out. And again, just trying to be careful of our units here. The only units in here are years, and so that's why this ends up being in years down here. Now, I'd like to be able to show that you can do this the other way as well. And you don't need to do this, but it's just hopefully helpful to have different options. But we have this other formula as well, using it more in terms of an interest rate. And so we think about it as an interest rate 1 plus p to the t power. We can also get that multiplicative factor. And what do we do? Well, we saw that with this particular example, the percentage rate was about 7. And so we do is 1.07 times the number of years. And again, we want to get this multiplicative factor of 10 times 10 to the 7, sort of like this here. Now again, to do this, I'll use this trick that we've been doing, which is I'll write 1.07 as the exponential of the log of 1.07. So over here, in this case, I'll write that as e to the natural log of 1.07, again, all that to the t power, which when I sort of bring that into itself, it gets to the e to the t, that is a t. E to the t natural log of 1.07. Again, that equals this multiplicative factor of 7 times 10 to the 7. And what do? Well, I take the natural log of both sides. So the natural log of this gives me t natural log of 1.07, and that's going to equal 7 times 10 to the 7. And so I can solve for t. Excuse me. Since I'm taking natural log of both sides, over here this is going to be natural log of 7 times 10 to the 7. So this is equal to natural log of 7 times 10 to the 7 divided by natural log of 1.07. When I did this, I got 266 years, which is a little bit more than what they're saying. And basically the reason is this rule of 70 that we've been doing, again, is a little bit of a fudge. So it doesn't work exactly. And if you go through and use our formula, the percentage rate that you actually get for this case here is a little bit different than 7. It's 7.17. And so if you plug that in, 1.0717, this comes much closer to that 260. But again, just trying to give you different ways of doing it. You don't have to be able to do it two ways, but hopefully that helps.